Furnace transformer short circuit. Electric arc furnaces are used for melting processes with the heat produced by an electric arc burning between the electrodes. The main electric component of the furnace is the step-down transformer. This is a three-phase transformer with a high current secondary connected to the electrodes. The arc electrical resistance is low, so the short circuit conditions are not unusual. The secondary and the primary of the transformer are connected in a triangle. The layers of high voltage winding are split into a number of sections, where each high voltage section lies between two low voltage sections. That is called sandwich winding. Our task is to estimate the transformer short circuit voltage, axial forces in the windings, and build the stray fluxes field picture. Okay, let's start QuickField now. In QuickField I create new problem. Transformer. Next. Problem type is AC magnetics. Frequency is 50 Hz. Model class is plane parallel. Length units are millimeters, and the core thickness is 292 millimeters. The problem database consists of the geometry model file, of the data file with material properties, and I will need also the circuit file to specify the winding connections. So I type in the circuit file name here, circuit 1. Finish. On the left you can see the problem pane, and on the right is the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the DXF file. DXF file is used by the majority of the CAD system to interchange two-dimensional geometric models. So here is the file, and I will open it. The model was imported. You can see we have the core, we have windings, but something is missing in our model. In fact, magnetic field is distributed not only in the core, but in the air outside. So we need to add the air to our model. Switch to insert mode. Zoom out again. Choose the line type to be half arc. Click and drag to draw the external boundary. Okay, now we should assign labels. For labels we will specify material properties. Switch to select objects mode. Click the object to select and type in the label name here. This is the air. Okay. Now let's zoom in. Switch the zooming mode off. And again I click here. To select multiple objects at the same time, hold the control button pressed. All these blocks are the core. So I type in the label name here, core. Here we have the sandwich winding. I will use the rubber band to select group of objects and hold the control button pressed to select multiple objects at the same time. Now, all these blocks are phase A primary, A plus. On the right will be primary, A minus. Primary, A minus. And the same rule is applied for the secondary. On the left, secondary A plus, secondary A plus, and on the right, secondary A minus. The same way we proceed with the phase B. these blocks are primary B plus, and these blocks are primary B minus. These blocks are secondary B plus, and these blocks are secondary B minus. And the same way for the face C. These are primary C plus, and these are primary C minus. These are secondary C plus, and these are secondary C minus. And we have the insulation between the layers of the windings. So I click here and type in the label insulation. And the same label I can use here and here. These are insulation. Here and here, these are insulation. And we have the insulation here. Okay. That's all for the blocks label. In our model we have 7677 blocks, and all these blocks are labeled. But we should also assign labels to the boundaries. So at this boundary I will assign label external. Now let's assign physical properties to these labels. Double click the label name in the tree and type in the magnetic permeability value. For the air I specify relative magnetic permeability of 1 and nothing else. The same for the insulation, 1. For the core I can specify nonlinear BH curve, or I can specify constant magnetic permeability. In our case it is 1000. The core is laminated, so I do not specify electrical conductivity of the core. Primary phase A minus. The winding is made of copper, which has the magnetic permeability of 1 and electrical conductivity of 56 megasiemens per meter. I should not specify any source here, because we have the co-simulation with the electrical circuit, and all conducting blocks from the model should be included in the electrical circuit, and the field sources will be specified in the electrical circuit. Well, the label primary A minus is assigned to many conductors, and here I will specify that these conductors are connected in series. This means that total current in each conductor will be the same. Okay. The same material properties I assign for all other winding labels: permeability, conductivity, conductors connected in series. Far away from our transformer, the magnetic field fades to 0, so I will assign 0 magnetic potential at the external boundary. OK. That is all for material properties. We have only to build the finite element mesh, just press this button, and the field simulation part is ready. Remember, we have the electric circuit. So I open the circuit file. It doesn't exist. Yes, I will create it now. And here I should place all conducting blocks from the model. Primary A+, primary A-, primary B+, primary B-, primary C+, primary C-, and the same for the secondary. Secondary A+, secondary A-, secondary B+, secondary B-, secondary C+, secondary C-. The short circuit test of the transformer consists of applying some reduced voltage value to get nominal current in the primary, and the secondary should be short connected. I will simulate this condition by specifying nominal current in the primary and short connecting the secondary. So here I will insert the current source. And the current source value is 25 amperes, which is root mean square value. And in QuickField I should specify the magnitude. So I will multiply it by square root of 2. OK. The same for the phase B. Properties 25 multiplied by square root of 2, and the phase is 120 degrees. OK. And for the phase C, same magnitude, 25 multiplied by square root of 2, and the phase is 240 degrees. OK. Now I will use the wires to connect the winding in a triangle. Here, here, and here. And I will connect the secondary in the triangle. And the secondary will be short connected. And I will connect in the triangle the 3 phases current sources. Now let's save all simulation files and run the analysis. The problem has been solved. Let's take a look at the results now. Here you can see the magnetic field lines and the color map of the current density. You can adjust the field picture. For example, I will switch on the vectors of the flux density, and I will switch on the color map of the flux density. I can use the probing tool to get exact value of the flux density in any point. Just click any point, and here is the flux density. There is another option to measure values. I can use the contour tool. First let's zoom in. Switch the zooming mode off. Now I will draw the contour line here and can get the flux density distribution along this line on the XY plot. You can also see the data used to build this XY plot in a table. Coordinates, flux density. You can adjust the tabulating step and get much more detailed result. OK. You can also use the contour tool to calculate integral values. Click the integral calculator And here I can calculate the magnetic flux or the cross-section area. I can also construct contours by selecting blocks. Let's again zoom in. And here I will select the secondary winding conductor. Just click inside and then conductor is selected. For this conductor I can calculate total current, I can calculate joule heat, and I can calculate the force. You can select multiple blocks and get the net joule heat value and the force. Please note that all field parameters are harmonic functions changing in time. Field lines are displayed for some specific moment of time. And for the color map you can use momentary values, root mean square values or peak values. The default is RMS values, as you can see it here. You can switch on the animation and see how the magnetic fields is changing in time. Let's zoom to fit, and remember we have the electric circuit, so you can take a look at the results calculated in the electric circuit. Here you can calculate the current and the voltage for each element. And if you add these complex numbers together you will get the short circuit voltage. Here you can see in Excel I used these values to calculate the total short circuit voltage of the phase A. On our website you will find more tools to operate with complex numbers. For example, I know that the voltage is minus 216 and the current is 25 amperes multiplied by square root of 2. Here you can calculate the impedance and the consumed power. We have the inductive loading with a power factor of 0.7. If you search for the furnace transformer on our website, you will find the example page. Here you can read about problem setup, browse the solution sections, take a look at the results, and download the simulation files. The simulation files may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.